Hello. So my name is Brian Ferrari, and today we're going to do week 2 of the astrochemistry webinar, the Tuesday episode. So today we'll have Dr. Ryan Fortenberry from the University of Mississippi giving a talk on quantum chemistry and spectroscopy, a match made in the heavens. So this webinar series was organized by me, Brian Ferrari, the UCF AVS chair, and Katie Slavichinska, UCF AVS Vice Chair. So this is done with UCF, the University of Central Florida's American Vacuum Society student chapter. And we're really excited to bring this to everyone. Glad you guys could all join. So the format of the webinar is a 45-minute talk by our speaker and a 15-minute Q&A session afterwards. When you ask the questions, we ask that you ask your question in the chat, because we do have a lot of people that attend, so we don't want to try and have the hassle of unmuting and muting people. So just ask the question in the chat. Our speaker will read through the chat and answer your questions in whatever pace they can handle answering. So today's speaker is Dr. Ryan Fortenberry, and Dr. Ryan Fortenberry is an assistant professor of physical chemistry at the University of Mississippi. He previously held the same position at Georgia Southern University from 2013 to 2018. Ryan earned a BS in mathematics and an MS in communication from Mississippi College, a PhD at Virginia Tech in theoretical chemistry, and was a NASA postdoctoral program fellow at the NASA Ames Research Center in Mountain View, California. Ryan is currently the chair of the ACS Astrochemistry Subdivision and the Ole Miss campus coordinator for the Mississippi Space Grant Consortium. Ryan has over 100 peer-reviewed scientific publications, received several NASA grants, and has published in Scientific American, and is the author of Complete Science Communication, a text on how to write and talk about science, both to expert and non-expert audiences alike. So again, he's going to be speaking on quantum chemistry and spectroscopy, a match made in the heavens. And I'm sure you guys are all just as excited as we are to hear his talk. So without further ado, I'll go ahead and stop sharing and let Dr. Fortenberry take over.
All right. Thank you, Brian. And thank you all for the invitation to be here. I'm very excited to be here talking about my favorite thing in astrochemistry. So let me get my screen up. All right. Everybody see that? Slides up. Looking good? Okay, very good. So let's get into this. Again, I really love to talk about astrochemistry. I enjoy this a whole lot. When I was in graduate school, the story I always tell is that I went to Virginia Tech. I wound up having a great time, but when I got there, oh my gosh, I was miserable. I was doing quantum chemistry, which was, yeah, kind of cool, but then it got really hard, and I couldn't figure out what I wanted to do. But luckily, I was fortunate that my PhD advisor had some experience in some different areas of physical chemistry. And I came to him one day and said, you know, Dr. Crawford, I don't want to do this anymore. I'm not enjoying graduate school. And he said, well, Ryan, what is it you really like? And I said, well, I really like space. And he said, have you ever heard of astrochemistry? And I said, no, tell me more. And so the rest is history. And so that's kind of where I got into this. And so I come to this from a quantum chemical perspective. I have learned a whole bunch about astronomy and made some good friends in this area. And I think that we have a really unique focus in quantum chemistry to help astrochemistry. And I'm going to talk about some of the things that I have done, and I would love to hear some of your questions, and I would love to discuss that with you here at the end. All right, so whoops, and here we go. All right, so let me tell you a little bit about the University of Mississippi. I am from Mississippi originally, so I think it's one of the greatest states in the country. For those of you who don't know where Mississippi is, we're down here in the southeast. Florida is over here. And the University of Mississippi is in Oxford, which is in North Mississippi. And it's named Oxford for that town in England where that other university is, such that we actually have a couple double-decker buses that come around town. And we have a festival every year called Double Decker Festival, where we have bands and all kinds of things that come to the center on the square. Here is the Lyceum, one of the main buildings that we have here on campus. It's a beautiful campus. We have trees everywhere. It's also known for athletics when we can have those. So this is a picture of Vaught-Hemingway Stadium where the football team plays, and my office in the chemistry building is just behind the scoreboard, right there in the back. And so I actually, when I go to work, I park there at the football stadium. And it's also considered to be one of the best places in the country for tailgating when we're allowed to do that. And so this is what the Grove looks like on a typical Saturday during a home game when Ole Miss is playing, and my office is right across the street from there. So it's a wonderful place to work, a wonderful place to be. We have great students. In the summer, I teach a yoga class for our undergraduate research students that come. And I had a student who was on the volleyball team as well, and this is what my daughter thinks of volleyball. So enough about Ole Miss. Let's talk about some astrochemistry. So I like to give this picture of an artist's rendition of the Milky Way galaxy, where we think we live in a nondescript planet around a nondescript star in a nondescript part of a nondescript galaxy. But yet, we're here, and we can think about everything else that's in the universe. And one of the things that we can think about is what molecules are out there in space. So I came up with a saying a long time ago. If you can think of a molecule, any molecule, take anything from the periodic table you want. There's a finite probability that over the immensity of space and in the eons of time, that molecule has existed somewhere. Now, the question is whether or not we can detect it. So here's a terrible picture, and the reason why it's a terrible picture is because I took it in the Guadalupe Mountains National Park Thanksgiving a couple of years ago. And if you squint really hard, you can kind of see 3 stars there in the middle that'll look familiar. And those are the 3 stars of Orion. So if we're wanting to look at new molecules in space, Orion actually has an object down here where we can train our infrared spectrometers and even our visible light spectrometers and telescopes to look at it. Now, if we come down here into the scabbard part of Orion, where he has his club or his scabbard or his quiver, depending on which brand of the image in the mythology that you ascribe to, in this true color Hubble image, you can see the Horsehead Nebula, which is part of the Orion Expanded Nebula. And it's got these beautiful purples, but it also has this black feature. And that black is made up of dust and molecules and other things in there. And of course, what's the pink? If anybody's ever done a hydrogen lamp experiment, you know that that's hydrogen gas that's being excited electronically. Now, if we switch this from visible and we take another Hubble image in the near infrared, we get this thing with this false color image. As you can tell, the pink is now all gone away, and that's now clear. And the opaque portion in the visible on the left is now giving off emission in the right. So these are the images of this. Now we can take a spectrum of this emission, and in a place that's close to this, in the Orion bar, we get a spectrum that kind of looks like this. Again, this is infrared emission. And each one of those peaks is caused by a molecule, or maybe a molecule and its cousin, or maybe something that's closely related to it. We're not totally sure what can cause all of these emission features in this infrared spectrum. But we have some new tools at our disposal. Now, experimentally, people like Brian and Katerina and many of you, I imagine, do experimental astrochemistry. And you have to synthesize these molecules, and you have all of this difficulty associated with making sure that you have low pressures and cold temperatures or whatever environment you're trying to simulate. But quantum chemistry, we don't have to do that. We have other things we have to consider. But we can truly study anything we want. So if we want to figure out what are the molecules that cause these emission features, we have a wonderful tool in quantum mechanics that can help us shed light on whatever these might be. So how do we do this? Well, again, I'm not limited as a quantum chemist by materials I can buy, by materials I can synthesize, by the apparatus that I have to use, by the wavelength of light or the spectral windows. I can make anything. And so I think of this as Legos, or in my particular case, as Connects. I played with these things all the time as a kid. You can make anything you want if you have the right pieces. And so here's a picture of a truck that I made with my daughter a few months ago. And we could take these small pieces and we can make a truck. Just like in quantum chemistry, we can go to the periodic table and say, I want an atom of carbon, and I want another atom of carbon, and I want a fluorine, and I want a magnesium, or whatever it is. And we can stitch it together, and we can come up with our own unique molecules that we might say could exist in space. They may have existed over the eons of time, but now we have a means of being able to detect it. in order to provide data quantum chemically. So that's kind of the background. How do we do this? I'm a quantum chemist. I got to show a couple big scary equations. But for many of you, this is just a Hamiltonian. This is what we call the Watson Hamiltonian. It's a row vibrational piece where we have kinetic and potential terms. And we also have places where the vibrations and the rotations interact with each other. So we have the kinetic and potential terms, the kinetic and the kinetic potential terms on the right. And then we have our pure potential, which we represent as a fourth order Taylor series expansion, because you can go out to an infinite Taylor series expansion where you have infinite derivatives of your function, and that will eventually describe your function. But we choose to stop at fourth order because when you go to higher levels, it's more complicated to do. But if you go to lower levels, you don't get an adequate description. And so fourth order is kind of that sweet spot. The way that we calculate this potential, we have to have these force constants, and we get these force constants through numerical differentiation. The first thing that we have to do is we have to get an optimized geometry. So we take all of those connects, we put them into our quantum chemistry program, and we get the best way that those atoms can be arranged at very high levels of theory, where we include core electron correlation much of the time. Then we generate our points that will describe our potential energy surface that we can fit to create our force constants in our Taylor series expansion. And then we calculate the energies at each of those points, which we then do our fitting, transform our coordinates, and then we're able to generate our vibrational frequencies, most often through vibrational perturbation theory. So that's kind of the theory behind what we do. So let's talk about astrochemistry and the things the types of molecules that I've been studying. So we like to talk about carbon sequestration here on Earth, and we like to talk about getting the carbon dioxide out of the atmosphere, but the universe has been sequestering carbon since carbon was made. If we have a star, here's one of my favorite stars, the sun. And so if we have a star, once the star is done burning hydrogen into helium, it will get to the point where it's making carbon, nitrogen, and oxygen simultaneously. Most of the time, oxygen is more abundant than carbon. This has to do with the stability of oxygen-18, the oxygen-18 nucleus, and the instability of nitrogen-17. But most of the time, we have more Y than X. This is just a simple limiting reagent chemistry problem that we all learn in the first 2 weeks of general chemistry. But what typically happens, and this is a gross approximation, but what typically happens is that carbon becomes your limiting reagent. Carbon and oxygen form together to make carbon monoxide. And then as the rest of the oxygen is flying out, what's it going to make? Well, it's going to hit all that hydrogen that's there, and it's going to make water. There are some circumstances, however, where you get more carbon than oxygen. They're rare, but there are circumstances where it happens. The classic star IRC 10216 is one of those. But when this happens, you're still going to make carbon monoxide. And you're going to make, at this point, because Y is your limiting reagent, you're going to make Y carbon monoxide. So what's the rest of that carbon going to do? Well, eventually, we think it's going to get processed into polycyclic aromatic hydrocarbons. And I've drawn it, and I've written it as such, where N and M aren't necessarily related. You can get aliphatic structures, and there's a lot of research that's going on in that area. But my point is, if you want to study astrochemistry, we typically think that carbon is so important, and it is, because it does all kinds of things. But most of the carbon in the universe is locked up in carbon monoxide, and most of that which is left is locked up in PAHs. Now you can break down PAHs, it's not easy, but you can break down PAHs. But my point is that most of the carbon in the universe is not really available to do chemistry. In fact, you might say that we're looking at the crumbs of carbon that are left over if we just stick with carbon. So what's some other chemistry that we can do with things that don't include carbon? As well as what's some chemistry we can do with just the PAH portion. So I've been doing a lot of work on PAHs. We believe that many of these emission bands are caused by PAHs. And here's pyrene, a classically small pH. For me, it's gigantic, but it's classically small, but we believe it can be made from cyclopropanylidines adding together. But in all of those peaks in that background infrared spectrum and that emission, we're going to get some from small carbonaceous molecules. We're going to get some bigger ones. We're going to get some ones that are even larger than this. So how can we study this? Well, remember that equation that I gave you where you had to have all of those points? To do that for this big pyrene molecule requires 13.4 individual quantum chemical calculations. It's insane. We're working on ways to shorten this. But one of the things that we can do, instead of looking maybe at the PAHs, let's look at molecules that aren't cyclopropanoidine, but maybe things that could ultimately lead to PAHs. And one of those has been this molecule where we just put a carbon on top of the cyclopropanoidine. We were able to use a lower level of theory, F12TZ, so explicitly correlated couple cluster theory, as opposed to this giant CCCR thing that I worked on in graduate school and as a postdoc. This molecule has 3,800 points that we have to calculate, which is non-trivial, but it's not 13.4 million. But if we use this lower level of theory, we're only in error by about 2 wave numbers. So that's not great for making astrochemical comparison, but it's perfectly fine for comparison to experiment that can then make application to laboratory experiment, which can then look at observation as well. One of the things that's interesting about this molecule, though, and of course I've drawn it with sticks. Now, if you were in organic chemistry class, there would be a double bond down here, and then there would be a double bond up here. And one of the things that I found was interesting is that if we look at that particular vibrational frequency, where those 2 double bonds are bending, it's an A1 mode, where they're bending, stretching, where they're stretching at the same time, that emission feature actually falls right there around 5.7 microns in this known region that's typically associated with polycyclic aromatic hydrocarbons. Of course, PAHs have all these conjugated double bond pi systems that are all throughout. This is one of the smallest molecules you can have that's both cyclic and has that same double bond alternation. If we look at the one where the bonds, where one is squinching and one is stretching, that is slightly, red shifted, and we get another emission feature that's similar to a PAH. Oh, that's kind of cool. Nobody's looked at this molecule before. This molecule has had exactly 1 paper that I was able to find written on it. But we were able to generate some data quantum chemically that no one's been able to see before. Another interesting thing about this molecule is that it has a dipole moment of almost 5 to pi, which means you can observe it from the ground with microwave spectroscopy. So if you combine microwave and infrared, you might be able to make a unique detection and a unique supposition about the carriers of these particular infrared emission features. But we still need to go to PAHs. These are just 2 tiny bands. There's hundreds of these things. So if we want to be able to do these 13.4 million coordinate force field points, I have a way to do that. I'm not going to tell you about it, but I have a plan. Not like Julia Stiles' plan, but I have a plan. If you don't get the joke, ask your parents. All right, so that's carbon. If we go to the periodic table, there's all kinds of things that we can look at. Of course, we know this as chemists, but one of the things that's frustrating is we're limited in astrochemistry. This comes from Ben McCall in a paper he did about 15 years ago. And he calls this the astrochemist's periodic table. And the size of the box is proportionate to the amount of material we have for each of these elements. So most of the universe obviously is hydrogen. Then we have a good bit of helium. And then we've got all the other stuff. So there's about 11 elements in here. But one of the problems with these 11 is that 8 of them are noble gases. And everybody knows you can't do chemistry with noble gases. And this is one of those cases where everybody is wrong, because you can. And one of the things you have to remember, though, before you start doing noble gases, is if you take the atomic symbols for all of the noble gases and you put them together like this, you can make a really funny anagram. And this deals with anybody who studies noble gases. He near crazy. So anybody who studies noble gases is nearly crazy, but maybe not so much, because there's this object. So this is the Crab Nebula that was originally observed by the Chinese astronomers in the Dark Ages of Europe. Europeans didn't see it, but the Chinese did. But we have the Crab Nebula, and it's been 7 years ago now, where a group was able to get some spectral data from a telescope that pointed at the Crab Nebula, and they found an amazing little molecule. They found argonium, ArOH+, the first naturally occurring noble gas molecule. And as a quick aside, people have hypothesized forever that argonium should exist in space because argon is super polarizable. As a matter of fact, argon is not as ideal of a gas as you would think. Helium is super ideal as a gas, but N2 actually functions more of an ideal gas than argon does. And if you don't believe me, look at the van der Waals constants for the van der Waals gas law equation. But anyway, they said argon should be polarizable enough to bind with a proton. And they were looking for this thing and looking for this thing and looking for this thing, and they couldn't find it. They kept finding this other peak, this rotational peak, that was frustratingly close to what they thought was supposed to be for argonium, but they couldn't match it up. And then it took longer than it should have, but finally somebody realized that the mass of argon in space that you get through alpha process of stellar fusion is argon 36, but the mass of argon that we have on Earth, which is a result of nuclear decay of potassium in the Earth's oceans, is argon 40. So they had argon 40 data, and were trying and kept seeing argon 36 data, which is a kind of a funny thing when you need the astronomers and the chemists to actually talk together. But anyway, they found argonium in space. This revolutionized my mind. I thought this was great. So I took that big giant equation I showed you at the beginning of this discussion and said, let's put all of these noble gases and let's see if we can make some molecules. And so I said, hey, if they found ArOH plus, maybe there's ArOH2 plus. And then we did it with neon. And then I said, well, you know, if they do it with H2, maybe we can do it with H3. And there's actually some experimental data on that that we were able to compare with quite nicely. And then I said, okay, Brian, stop being stupid. Make that argon bond to something. And so I said, well, let's have something that's going to pull the electrons off. And what's going to pull the electrons off? Oxygen. Oxygen's going to pull those electrons off. So we did a study on ArOH plus. Finally convinced one of my experimental colleagues at the University of Georgia to go look for it. He did and found ArOH plus in his laboratory experiments. And we were able to do a prediction of that and give him the spectroscopic data necessary for that detection. Put a nitrogen in there, then we did some stuff. This is crazy when you have an ethynyl group and a neon, it actually goes zigzag. Argon stays linear, and then we did an ArCN as well. You know, lots of noble gas molecules. I kind of ran down this rabbit hole for a long time, but all of these are well-bonded species that have non-negligible amounts of covalent bonding between the argon and whatever the ligand is that's beside it. And then there's this guy. I like this one a lot. I like to play with my molecules the same way I play with my food. And if you look at it carefully, what you'll see is that you have a neon, an oxygen, and a nitrogen. And if you arrange those letters just right, that spells out the word neon. So neon is both an atom and a molecule. That was the title of that paper, which has been a lot of fun. Well, let's talk about a specific class of noble gas molecules that are really kind of cool. These are called proton-bound complexes. And the reason why these are interesting is because you have a proton stuck between two ligands. It doesn't have to be noble gases. I've also done this with N2 and CO and a few other things. But if you stick it in between there, your total mass in space, when it's argon 36, is 73. On Earth, it's 81. It's not that big of a deal. But you have a proton in the middle, and most of that charge, nearly all of that charge, is located on that proton. But almost none of the mass is. And so as this proton bounces back and forth in this particular vibrational mode, what happens is you get an infrared signal that lights up like fireworks. And according to Beer's law, get it, Beer's law? Beer's law, you don't need much concentration. You don't need much concentration in order to get a detectable signal, because you have such a large change in dipole moment as all of the charge and nearly none of the mass is moving. So this gives you a bright signal, so you don't have to have large amounts of material in order to have a detectable signal. So we did some studies on this where we put argon and neon together, and we were able to show what that bright mode would be, and it shifts down to the, to the blue as you put a lighter atom on there, as you would expect. But then something else happened. So this is NGC 7027, so this is another cinder of a dying star. And an international group was able to take the Stratospheric Observatory for Infrared Astronomy, and they found HEH+. They found this particular molecule in the remnant region of this star, where the outgassing material is coming out and is interacting with things from the interstellar medium. So the helium and the hydrogen were able to bond together at that point when you have ionized helium. So this got me thinking, well, we did all these proton-bound complexes with argon. Let's do these proton-bound complexes with helium, and we find that we were able to show these. One of the things that's really interesting to me about this helium proton-bound complex is it's made of helium and hydrogen. No kidding. Who cares? Before stars formed, you had three atoms, three elements: hydrogen, helium, and tiny bit of lithium, so we're going to ignore the lithium, which means that if you have chemistry before stars, the only molecules that you could have are those that involve helium and hydrogen. If you have helium and hydrogen, we know that HEH plus formed during this time, according to all the models that we have that have led to chemistry. But if you can also form this He2H plus, you're going to get this really bright infrared signature. And even then, if this molecule could form, we could go back to the cosmic microwave background radiation, adjust for Z value, adjust for the redshift of like 1,000, some giant number. Maybe, just maybe, that band would show up. And that would be the first unique tracer of the early universe. We need more experimental data to do that, but we have generated quantum chemical spectral data to show where these could be, leaving it open for cold plasma experimental scientists to maybe look for this particular molecule's infrared signature. We've proposed a way in which this molecule might form through all of these pathways. We can start out with helonium, which we believe existed in the early universe. It can be hit with a helium. It goes down in energy. Of course, radiative attachment has lots of problems, including how do you get rid of the kinetic energy. So there is a total energy gain, but what's the energy cost before you get there? But one of the other things that we were able to show, new to science, was down here, where we have He2 plus, which is also hypothesized to exist in the early universe. You're not going to see it in the infrared. You're not going to see it rotationally because you don't get any type of dipole moment, whether it's permanent or induced. But we were able to find for the first time that there is a very shallow well for this particular triplet structure. And then you get this huge energy gain to go into the steady medium, the steady minimum of He2H plus. This is a Jacobi coordinate set. We're down here at the bottom. We have the distance between the center of mass between the two heliums and the hydrogen atom, and the distance between the two heliums. So this communicates that we have a linear structure for our singlet form, our He2H plus. Our triplet looks very different. The potential surface in these same coordinates looks very different. But if that proton is vibrationally excited enough to drive down into that portion where the two heliums can start to separate, these two can overlay on top of each other, and then you only have a minimum barrier to cross from this minimum to here, which you can do with photoexcitation, or certainly with collisions in the early opaque universe, where you could form He2H plus in that linear proton-bound complex. Maybe it's out there. Maybe it's another candle for us to be able to probe the outer parts of the universe. So those are kind of the things that we've done with noble gases. So let's talk about some other parts of the periodic table. This is Comet 67P. So we're going to go back to carbon and oxygen. And one of the things that was really surprising when Rosetta went out there was it found this molecule and this one and this one, and oh my God, there's so much O2. Where did it come from? Our models don't say where the O2 could come from. Oh my goodness, we might have some gap in our data. There's all kinds of O2 around this molecule in quantities that primordial O2 has not been able to show through the models that have been put together. So we put together a couple of hypotheses about these. One of them was that water will actually form a very strong bond with oxygen cation directly onto the oxygen. Something on the order of like 60 kcals. It's greater than the OO bond in hydrogen peroxide, which you can buy in a bottle. Granted, it's a cation, which means you can't buy it in a bottle unless you make it a salt. But you have a novel way in which you can make an OO bond. And we did some calculations about how you could pop off the H2. Maybe it's possible, maybe not. Who knows? Another thing that you could do, remember when we were going back to carbon sequestration, where most of the carbon is locked up in carbon monoxide? Well, if it's cold enough, you're going to make an ice. And this is some work that I did with our host and with Professor Bennett there at UCF. Where maybe when you have carbon monoxide and carbon dioxide ice, maybe as they sublime, you don't make pure CO or CO2. Maybe you get these intermediate species that are coming along. So here we were able to do some calculations on CO3 neutral. And what you can tell from this optimized, pseudo-optimized structure, this cartoon of the structure, is that you get a CO bond, you get that carbon monoxide, but then you also get this OO bond at the bottom. And if you look at this from a Lewis structure, The Lewis structure is actually beautiful because you get a double bond up here to this, and you make almost like a formaldehyde type bond, this aldehyde type bond, ketone. And then you have single bonds coming down, and the oxygens all have 2 bonds. So it makes a stable molecule. Nobody had done a significant amount of infrared spectroscopy on that one except for Professor Bennett. And so we were able to say, here are some infrared features for this particular molecule that may help to explain the formation of O2. So we've looked at noble gases, done some stuff with oxygen. Let's go back to this periodic table though. Tons of hydrogen, tons of helium. Everybody does stuff with carbon, and there's lots of oxygen. If we look at this elemental abundance slightly differently, let's take out hydrogen and helium. This is kind of what's left. This is in all of space, based on what we can observe. You'll see, yeah, there's carbon, but it's not a ton of carbon. Some nitrogen, there's a bunch of oxygen. Wow, some neon. Well, we talked about neon and argon. There's all this other stuff too. But let's not look just at space. Let's look at something else. We want to care about where life came from. So we need carbon to look at that. But life can't just exist out in the vacuum. You're never going to do those chemical reactions in high enough abundance. They're going to create amino acids. You got to have a surface. You got to have something for those things to sit on. So you need a dust grain or a rocky body. Well, okay. What's the composition of a rocky body? Let's go to our favorite rocky body, the Earth, the one that we're on right now. And the composition's completely different. What? Oh, well, of course, Ryan, that makes sense because the Earth is made of rocks. Yeah, the Earth is made of rocks. Most of those rocks are comprised of oxygen and silicon and magnesium with some iron and other things as well. So if we look at this model habitable rocky planet, the Earth, the only one we know of thus far, the mantle of the Earth, which is these red and yellow layers, you have the upper mantle and lower mantle, makes up 84% of the volume of the Earth. So that means a majority of the Earth is the mantle. Well, what makes up the mantle? So if we go to our periodic table, oxygen makes up 45% of the mantle. Silicon makes up 22%, and magnesium makes up 23%. Much of the rest is in iron and aluminum, as I showed you on that previous pie chart. So, rocks had to form planets. Well, those rocks weren't always great big rocks like the Earth. They were very, very small rocks for those of you who are Monty Python fans. It floats on water. No, just kidding. So you've got very small rocks, nanocrystals. So we've got these little tiny nanocrystals. And we know how to get from these small covalent, network covalent nanocrystals, we know how to get to dust, the stuff that's around stars as they're beginning the protostellar phase and beginning to create a disk and then making ultimately planets. We know how that happens. And we know that all the elements, magnesium, iron, silicon, oxygen, carbon, we know that all of those were atoms that were fused in the core of a star. How do we get from the atom to the very small rocks? Well, we don't know. This is mind-blowing. We have ideas, and some people say, oh, it's a gas of, ions, cations, and anions. It's a gas of these things that condense, and maybe that's true. But along the way, you're going to make some small molecules. You have to. You can't just go from atoms to nanocrystal. You have to aggregate these things together. And I would argue that being a quantum chemist, I have a duty to explore new types of chemistry, new types of molecules that nobody else can. And the understanding for how to synthesize organic molecules has been around since Justus von Liebig was the first modern organic chemist in Gießen in the late 19th century. But we don't have as clear of an idea how to do this for inorganic species, but we can do this computationally. So if we want to start with atoms and go to these small and medium-sized molecules in order to see what their pathway might be on the path to creating planets, we need to know what their spectra are, because that's the only way we're going to be able to observe them from the Earth. We can't fly a mission out to a nearby star and sample its protostellar disk. like we can send a mission to 67P in order to sample what's in its atmosphere. So we have to generate remote sensing data. And infrared spectroscopy is a fantastic way to do this with inorganic molecules. Another thing that can happen is that after the star has expended its energy, it's no longer able to create, below the Chandrasekhar constant, it's not able to burn any new elements after it's gotten done making oxygen. And so the star will expand, outgas, and then remain as a little tiny cinder. But in that outgassing stage, and this is what's going to happen to our sun, it's going to send out all this high energy material, and it's going to ablate all of the rocky inner planets, including the Earth, as well as Mars and Venus, and it's going to rip them all apart, and it's going to send their rocky materials into the gas phase again, just like an ICP-MS would. So there may be places where we can see the molecules that were made up of rocky materials as the star is expanding and dying. So we have two times, the early stages of star formation and the end stages of star formation, of stellar lifetime rather, not formation, where we may be able to see small molecules that share a lot in common with network covalent crystalline minerals. One of the simplest ones are magnesium oxide. Now, I got the idea to study magnesium oxide because I thought it would be funny. I had an undergraduate student who was coming to work with me one summer. And I said, oh, this might be fun. What are some fun molecules? Well, there's a lot of oxygen in space. There's a lot of magnesium. They're both divalent. Magnesium and O, MgO, MgO. There's got to be a joke here somewhere. And so eventually I came up with it. And it's, you're studying inorganic molecules? Yep. Like OMG. Get it? OMG, oxygen, magnesium. And anyway, I thought this was hilarious when I came up with it. But it turns out magnesium oxide is actually really important. Really important for geochemistry. Magnesium oxide mineral is the white material you see here called periclase. It is known in the Earth, and it is actually in the geologist major triangle for oxygen chemistry. You have magnesium, on the points of the triangle, you have magnesium, aluminum, and silicon with oxygen linking them together, and how they all form based on different conditions leads to whatever the minerals are. We'll talk about that a little bit. But with magnesium oxide, let's just look at the monomer. One magnesium and one oxygen. We were able to do some quantum chemical calculations that compare really well with the experiment, especially for this vibrational band here. But what does the dimer look like? If we're going to make a network covalent solid, we're going to start with a monomer, and then we're going to have a dimer and a trimer and a tetramer and blah, 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 until we get to one of those little tiny, very, very small rocks, one of those nanocrystals. So this is what the dimer looks like. It has no permanent dipole moment, so you're not going to be able to see this rotationally. But its infrared features are kind of interesting. As you can tell, let's just focus on the CCCR data for this magnesium oxide dimer. All of our vibrational frequencies that we can see are well redshifted mid-infrared and beyond into the far infrared. They also have really strong oscillator strengths. That's what's here in parentheses. These are the intensities for some, to give you some perspective. The antisymmetric stretch in water, which makes the atmosphere almost opaque in that region where it has its non-transition, is 70 kilometers per molecule. We're 3 times that here with this particular guy. And it makes sense. You've got, go back to the structure, you've got 2 magnesiums, really want to give away their electrons. 2 oxygens, really want to take in their electrons. So kind of like those proton-bound complexes, you've got something that wants to be positive, something that wants to be negative. And when they start moving around, you induce a pretty significant dipole that you don't normally get in organic species. So we tried it for the trimer. The level of theory we had available at the time wasn't very good, but we were able to show that you get, whoopsies, that you do get very large oscillator strengths as well. Moving on from magnesium oxide, just because it was the next thing in my head, we went to magnesium fluoride. Now, you've worked with magnesium fluoride if you've ever used a vacuum chamber. That's what natural magnesium fluoride looks like over there on the right. But magnesium fluoride typically makes the windows. It's this clear strong material. And the reason why it's clear is because its infrared frequencies are well redshifted. So there are some data for the monomer of this where, again, we compared fairly well with experiment. Now, of course, these are matrix data and they're about 40 years old. And so the resolution wasn't as good. But we get, for magnesium fluoride monomer, we get, again, fairly large oscillator strengths, fairly large intensities. This is what the dimer looks like. See, fluorine makes 2 bonds, breaking all the rules of organic chemistry. And we were, again, able to show that you get very intense bands for magnesium fluoride dimer. Now, magnesium fluoride doesn't have a whole lot of applications. There's not a whole lot of fluorine. So what are some other things that we could study? Oh, yeah, and JPCA liked this so much that they put it on the cover a couple of years ago, back in 2018. Let's go with a quintessential mineral. If you had to pick a quintessential mineral of the Earth, you would pick this guy. Picture that I took in Guadalupe Mountains National Park, like mountains. Another form of the same mineral is this guy. So on the left, we have quartz. On the right, we have ground up quartz, which is sand. Sand is silicon dioxide, comparable to carbon dioxide, except we have a silicon in the middle. And this is what the monomer of this would look like. Now, you're not going to see this on the Earth. But if you have a star that's dying, that's sending out tons of energy onto a rocky planet and ripping it to shreds, you're going to get SiO2 in its atmosphere. Or if you have Si and O that are in the gas phase, they're going to condense down, and you're probably going to make this before you go on to make the larger network covalent solid. We're able to calculate vibrational frequencies for SiO2 and SiO3. And SiO3 is analogous to that CO3 I showed you earlier in the work that I did with some of the folks there at UCF. We can compare with some matrix experiments for SiO2 where they compare fairly well. But again, we get these fairly large oscillator strengths. Again, so our computations for the infrared frequencies are pretty close. But the biggest thing is that these oscillator strengths are pretty large. Now, I mentioned periclase, magnesium oxide, is really important for geochemistry. So is quartz. We know it's everywhere. If you combine these two guys together in MgSiO3, you actually form a mineral, if you go onto the network covalent solid, that's instatite. And it's this brown crystalline material. This is what the monomer looks like. And so this is kind of the building block of all rocks on Earth, for all intents and purposes, because instatite is one of the major, and one of its cousins that I'll talk about in just a second. These are the major components. You know, when I showed you that thing that had the mantle is 84% of the volume of the Earth, and most of that is magnesium, silicon, and oxygen. It's mostly in this form, not in this particular molecule, in the one on the right, in a molten form within the mantle, of course. But if it cools, it forms this crystalline form. But anyway, this is what the monomer of instatite looks like, the lowest energy form of this. We did a bunch of studies where we looked at how we can arrange all of these atoms in different isomers, but this was by far the lowest energy form. We were able to calculate vibrational frequencies at fairly high level. And then Zoom's getting in the way. So we also calculated these at high level with anharmonicity, which is what you have to do to get it experimentally comparable. And we have large oscillator strengths in here, especially for these 4 particular bands. They're all above 100 kilometers per mole. It also has a dipole moment that's gigantic. And just like that C4H2, we could observe this in the microwave, and we can observe this in the infrared. We can observe this through rotational spectroscopy and infrared spectroscopy. So we were able to generate some of the spectroscopic data to create this simulated spectrum in the hope of maybe encouraging some ground observers to look for this molecule. Now, if we take another magnesium oxide and stitch it on here, we create forsterite, which is actually the most common mineral in the Earth's mantle. It's like, depending on certain studies and models, it's somewhere between 45 and 60% of the Earth's mantle is this particular mineral. When it's by itself, it's forsterite. If you put a little iron in there, and there's a ratio of magnesium to iron, you create what's generally referred to as olivine because it's green, like you can see from this particular image of olivine, forsterine olivine. Olivine, forsterite, olivine, I'll get it out. This particular molecule is the lowest energy structure of the monomer. There are a couple of others. It has a very large dipole moment, so just like the instatite monomer, the forsterite monomer is both vibrationally and rotationally active. And good gracious, these intensities are just off the charts. I mean, they're huge. And I'll talk about where those frequencies fall here in just a second. I mentioned this wasn't the only monomer. There's also this one. This one is actually closer to what you get in the network covalent solid because you have tetracoordinated silicon. Whereas in this lowest energy monomer, you don't, you have tricoordinated silicon. In this one, you have tetracoordinated silicon. It's higher by 10.3 kcals per mole, which is not negligible, but it's also not a whole lot. And we were able to calculate the vibrational frequencies here. And most notably, you get this huge intensity. I mean, this is just nuts. What's happening in that particular band is that if you think of it as the two magnesiums are free to move and everything else is locked in place, those magnesiums are shifting back and forth. If you think about it as the magnesium's locked in place, it's almost like a proton-bound complex again, where you have that silicon bouncing in between, where the silicon is much more electronegative than the magnesiums. And so you get that same motif of that antisymmetric stretch, giving you this really, really large intensity for this particular vibrational frequency. One of the things that's really cool about these molecules is that instatite has been conclusively observed in the Butterfly Nebula, which is what I have the picture of right here. And so in the study where they did this, they got this spectrum. Many of these bands they attribute to PAHs, and they would correlate with the Orion bar infrared emission spectrum I showed you at the beginning of this talk. But many of them aren't known, especially those from like 10.5 and 12 up to about 17 microns. So this is in microns. Nobody knows what they are. Guess what? These monomers fall in this range. So we have these two bands for the instatite monomer. Then we have these two really bright bands for the lowest energy forsterite monomer. Then we have the D2D monomer, where they're out here in these places where astronomers don't know what is causing those emission features. Interessante. Are these there? I don't know. Are they stable enough to exist before they go on to form this network covalent solid? I'm not totally sure. It depends on the conditions. But there's a coincidence here. We said, okay, we've been doing this with magnesium and oxygen. We've been doing this with silicon and oxygen. Let's try it for a whole bunch of other things. So we took the simplest motif that we can think of, 2 oxygens and then 2 of whatever else, we call them M, where you have magnesium, aluminum, silicon, phosphorus, sulfur, calcium, and titanium. And we're able to calculate the vibrational frequencies for these guys. And what you'll see is that the highest frequency is less than 900 wave numbers, which is going to put it well beyond 12 microns, 11 microns. Then you also have very large intensities, and the largest ones correspond to Si2O2, P2O2, and Ti2O2. But all the other ones for that nu3 bend are pretty large. And what is that bend? That bend is where you have the 2 oxygens and the 2 metals, we'll call them that right now, where the 2 metals are bouncing back and forth in that pseudo proton-bound antisymmetric stretching motion. We're getting large intensities with that particular motif. On top of this, we were able to show that we can take vibrational frequencies, calculate them explicitly, generate a scaling factor, which is what we did here for this magnesium oxide dimer, when we have stretches. Now, we also did the same thing for bends, and this is now the plane bend that I'll show you here, where we calculated it explicitly, and we got 2.834 wave numbers. And then we did a scaling factor where we averaged the differences for all of these bending motions, and then we did a separate class for the stretching motions. And if we apply those to our whole set, for this particular molecule, the mean absolute error is 2.2 wave numbers, so we're pretty close to experiment with that. And then we can take that and put it onto this molecule. Now, to calculate the quartic force field that I showed you earlier, even with this slightly lower level of theory, it took 10,000 CPU hours to do it. And that's what our QFF data are. If we take our harmonic values and scale it, that took us 40 CPU hours to do it. And then we just do this multiplicative factor onto it, and we only get an error of 1.6 wave numbers. The total for the set that we looked at was 3. But the reason why we're able to get away with this, one, is because these don't have large amounts of anharmonicity because you have heavy atoms. and two, because you're shifted out into the mid and far infrared. So the amount of error that we're introducing here is fairly small. So we could be off by large percentages, but the absolute errors are going to be fairly small. But still, this gives us, remember that thing where I said we have a plan? 10 things I hate about you. We have a plan. One of them is in getting very specific scaling factors for vibrational frequencies of particular classes of molecules with particular classes of vibrational frequencies. We're still working on that. We have some other tricks up our sleeve too. Okay, but and this also made the cover of JPCA. Yay, Ryan, you're so cool. Okay, anyway, let's look at these molecules that we've talked about with inorganic bonding, these things that are pertinent to the chemistry that led to rocky bodies like the Earth. Periclase, instatype, lowest energy forced to right, next lowest energy forced to right. There's a motif here. It doesn't take a rocket scientist or an astrochemist to figure out what that motif is, and that motif is oxygen. The way that I describe this is oxygen is the mortar between the bricks, and those bricks are all your other metals and heavy atoms and inorganic atoms. Silicon and magnesium in this case, but this also holds true with calcium, titanium. We've done it a little bit with iron. Oxygen is the mortar. If you have two heavy atoms, if you have two metals, two magnesiums, their bonding is weak. If you have two silicons, their bonding is weak. If you have two oxygens, their bonding is weak. If you have magnesium bonded to oxygen, it's strong. If you have silicon bonded to oxygen, it's strong. And so the reason why so many refractory materials have oxygen in them is because it forms strong bonds. And so this got me thinking, what am I missing? There's got to be something else. This can't be so straightforward. And this is where I've got a couple of slides here, but this is the last thing I want to share with you. And I have it last because to me, it's most important. I had a student, I said, he was a very young student. And I said, okay, I'm going to give you some monkey work. I want you to go calculate the bond energies of every atom to every other atom smaller than chlorine with the exception of neon. So I had him take all the atoms in the periodic table from lithium to chlorine and bond them together with a single bond, what we would call a single bond typically. And then we would fill the valence with hydrogens. So for instance, one of the things he calculated was the carbon-carbon bond strength of ethane. We say that's a fairly strong bond. According to our calculations, and these match experiment quite well, it's about 84 kcals per mole. Which turns out it's not the strongest thing that you can have. The strongest thing that you can have is actually beryllium fluoride. What? This is crazy. Why is it beryllium fluoride? That doesn't make any sense. It's HBEF, and we're breaking that BEF bond. It's 174 kcals. This is nuts. The next strongest one is basically the same thing, but without beryllium, but with boron. Why? I don't know. And frankly, I don't care. And I'll tell you why I don't care. Because I'm not a fundamental chemist, I'm an astrochemist. Beryllium and boron are notoriously depleted in the interstellar medium. So is fluorine. There's more fluorine than beryllium and boron, but there's not much. Okay, so let's take out beryllium, boron, and fluorine. Okay, the three strongest things that make bonds, apparently. And if you look carefully at the data, you're like, oh, you're going to get periodic trends. It's going to get stronger when it goes to fluorine and blah, blah, blah. Not quite. There's an island of stability right here. The strongest bond on the periodic table, single bond on the periodic table, is actually between aluminum and oxygen. I've heard inorganic chemists say all the time that aluminum really, 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 really likes oxygen. Yeah, aluminum really likes oxygen. It's got a bond that's 50% stronger than the bond in ethane. Huh. And not only that, if we take away fluorine and beryllium and boron, the next strongest bonds are with oxygen and magnesium, oxygen and silicon. Huh. Curious. Because if we go back to the abundance of the elements in the Earth's crust, it's oxygen to magnesium, oxygen to silicon, oxygen to aluminum. Are these two things related? I don't know. It's a fascinating coincidence. Why? Well, There's a whole bunch of reasons why. So we did an SAPT2 calculation, which basically just rips everything apart into electrostatics, exchange, induction, dispersion, various ways that the interaction between your two pieces can interact. You're not going to get anything from these tables. That's just for the reviewers of this paper. Let me show you what really matters. I'll make it black and white. What we were able to find was that if the ratio, this delta EL to I, the difference between the electrostatics to the induction is high. What this means is that the electrostatics, so just the pure charged interaction between these things, pure charge attraction of these things, is really high. And the induction, which is where the orbitals are shifted and moved in response to one another, is really low. Because when you change the positions of the orbitals and you create what we would typically think of as covalent bonding, you're actually creating dispersion and exchange, which makes your energy go up, and it's anti-bonding at that point. But if you have basically all electrostatics, this correlates almost perfectly with the bond energy. So aluminum oxide is a highly ionic bond, or some would call it a polarized covalent bond. But regardless, it has a large amount of electrostatics. This makes the bond super strong. So what we're able to conclude from this is that the most abundant elements in the universe and those that make the strongest bonds, if you get in that Venn diagram, if you get that middle place, those are the elements that are most common in rocky bodies. And this just blows my mind. So, astrochemists like carbon. Yeah, it's a great atom. It does a whole bunch of chemistry, but it's really not abundant. It's really kind of the crumbs. Maybe oxygen is super important, and maybe we can find some new chemistry studying it. All right, so that's the end of my talk. I want to give you all updates about a couple of things that are coming up. So we're going to have, this was originally supposed to be in 2020, but we had to reschedule it. So we have sociological implications for astrobiology will be held here at the University of Mississippi. And also we have Pacific Chem coming up in December, hopefully in Hawaii, where we have an astrochemistry symposium that I'm helping to organize, and we still have abstract submission open. We would love to have some of your contributions if you're able to join us in lovely Honolulu. So with that, I'd like to thank my group, especially my undergraduate students and my graduate students who make this so much fun. If you like my talk, I wrote a whole book about how to give talks. I also wrote an article in Scientific American because I like to communicate written and orally. This came out back in February, so tell all your friends about it. And I like to climb mountains, as you can tell. So here's a picture of me on top of a mountain. And here's a picture of me on top of another mountain. Since I'm giving a talk sponsored by UCF, I figured I'd show a picture of the highest point in Florida, all 345 feet of it. And with that, I thank you so much, and I would love to take any questions that you might have. All right. So let's see what questions we have. All right, so the first question I have, and I'll stay here and answer questions until my kids come up here and make me entertain them for a little while. Okay, first question that I have in here is from Ryan, great first name, Galinkin, I hope. He says, after H2 and H3, what would you suspect are the top 5 most abundant molecules in the universe? Excellent question. So definitely H2, definitely H2. The current consensus right now is that the next most abundant molecule is carbon monoxide for the reasons that I explained. Then it gets into splitting hairs as to what's a molecule and what's not. You know, there's the story that some of my colleagues like to ask. If you have a tire, how many molecules make up that tire? The answer is 1, because it's a giant polymer, and it's just one single thing that's got the carbons bonding closer and closer and closer and closer and closer together. And so then the question is, if we have, you know, a dust grain, for instance, that's pure silicon dioxide, that could technically be 1 molecule. Okay, but let's not split those hairs. I'm just saying that could be it. All right, so definitely H2, then CO, probably H3 plus. Some survey, and then you get into the question of, is it most abundant? What you can see is most abundant, or is it just what you have reference data for? So H2, CO, maybe H3 plus. Some surveys say that C2H, ethynyl, is one of the next most common molecules. Then we start getting into other things like NO, potentially N2. We actually haven't conclusively observed N2 because it doesn't have a permanent dipole moment, and it doesn't have an inducible dipole moment because it's a homodiatomic. So potentially it could be N2. The thing with carbon is that, again, it makes PAHs, and there's not one unique molecule that carbon is really going to do on its own. You're going to make, you could make pyrene, which I showed you the picture of at the beginning, has 4 rings, but you could put another carbon on there, you could put another benzene ring on there, and its properties are going to be similar but slightly different. But basically, H2CO, probably H3+, HCO+, maybe N2H+. And HCN. Those are the ones we typically use as tracers of gas in the interstellar medium. So it would be those. H2, CO, H3+, HCO+, HCN. Those are going to be your top 5 probably. Okay, next question from Jen Brunkman. Have ALO, SIO, and MgO been detected in stellar atmospheres? SIO has. SIO has. I don't recall off the top of my head if aluminum oxide has, but I'm pretty sure it has. I think ALO has. MgO has not. And I know that because I was talking with Jan Kami at the University of Western Ontario about potentially looking for MgO. I forget which star it was. It was a classic KGB star. That's the Russian Secret Service. I forget what it is. Sorry, my astronomy is not perfect. But SIO has, I'm not sure about ALO, and I know MgO has not. Okay, so here we have another question from Siddhant, an undergraduate from India, as he calls himself. What computational suite and programs did your undergraduate research students use to react one molecule with another and calculate energies? So excellent, thanks for the question, Siddhant. So the stuff that we're doing, I'm not necessarily interested in the reactions because that's typically what we call dynamics. We can calculate, a minimum energy, change the atoms around, calculate another minimum energy. And so that would give us relative energies, but the reaction energy, you have to go through the transition state, and we typically don't do that. But we use all kinds of classic quantum chemistry programs. Typically we use MolPro, C4, and Psi4. But we've also used, obviously we use Gaussian a good bit as well. And I know I'm forgetting another one. We've used NWChem too. But each one of the programs have different benefits. MolPro has an exceptionally fast couple cluster code, so we use that when we're doing these high-level couple cluster calculations. Psi4 has availabilities, and C4 have availabilities that other things do not, and so does Gaussian. Really, with any of the codes, the hardest thing, once you have it installed, it's just learning how to generate an input file. So Siddhant, the thing that I would encourage you to do if you're wanting to do more computational chemistry and quantum chemistry is just look at sample input files, figure out how to generate those for the particular program, and know what program you need to use based on what type of properties that you're wanting to get. So excellent, thank you for the question. All right, Chris Bennett is asking, why does NeON have a 90-degree angle? This is great. Okay, so it's right. NeON, neon cation, is L-shaped. So the way that the orbitals on nitrogen and oxygen are created when they go into that structure, if you think of the Lewis structure of NeON+, you think that it's going to be isoelectronic with N2, where you're going to get a pi bond that's going to be, you're going to get 2 pi bonds that are perpendicular to each other. But because oxygen is slightly more electronegative, what it does is and this is hand-wavy argument, but what it does is it creates a slight hole in that orbital space above the nitrogen in a p orbital. And so then you have this distended p orbital that gets struck out. I forget, David Woon has talked about this type of molecular orbital theory. I forget what it's called off the top of my head. But you get an additional amount of empty p orbital off of that nitrogen atom. And so it's going to, that neon and the lone pairs on that neon are going to preferentially bond to that nitrogen in a p orbital shape, which is why it's 90 degrees. And we can talk more about that if you have more questions. Okay, Rodrigo asks the question, ALO, SiO, and MgO could have some importance to astrobiology. You bet, you bet. We need magnesium, obviously, in order to engage in the biochemical processes that we have here in our bodies and in biology that we need for general, that we have in general that go on. I'm not a biochemist, so I don't have any additional comment on that, but definitely they could, because we have, we have to consume salt. Sometimes we do too much salt, but we need the magnesium salts in our body in order to regulate our electrolytes and various other things. I'm not sure about aluminum and silicon. I know they have some need in biological processes. But for me, the way that I think about them is we need solid surfaces in order to do biochemistry that lead to life. And so we need structures, dust grains, and they're going to be comprised of aluminum oxide, magnesium oxide, silicon oxide, and those types of things. And not even just dust grains, but rocks in the earth and larger bodies, rocky planets where we can have life. Okay, Ankan Das has a question. The rate of formation of ArOH plus, NeOH plus, and HeOH plus is very low. What do you think about their identification in the crab? You're right. The formations are very low. It's a balance between, obviously, between how quickly it can be created and how quickly it can be destroyed, and that has to do with the bond strength. The bond strength in HeOH plus is very low. Helium just doesn't like to do anything. NeOH plus, the bond strength of that is like 15 to 20% that of an OH bond in water. So it's not very strong. So I would say that you're not going to see NeOH plus. There is a chance you could see ArOH plus. I mean, you can form HeH plus in NGC 7027, the Dumbbell Nebula. And its rate of formation is pretty high because you have a lot of pressure. Now you have less argon. You have tons of hydroxide cation, but Ankan, you're going to have less argon than you're going to have helium, so that's probably going to slow it down. Where they found ArOH plus was actually in a region that was super ionized, and the argon actually gets ionized in that process, preferentially over the H2. So in places like that, you probably could, and some people say that ArOH plus is a tracer of almost pure atomic gas. Maybe ArOH plus could do the same thing, but it does form a fairly strong bond. It's just a matter of getting something to pop off the other side to take the kinetic energy away. But ArOH plus, probably the only one of those three that you could find. Okay, so Suzanne Wampfler has a question. And she also gives a big shout out to the organizers for putting this together. All right, so Suzanne says, do I have a wish list of what I would like observers to search for? Oh, man. Oh, that's a great question. Everything I told you in this talk. The reason why I say that is, as a quantum chemist, I spend all my time sitting behind a computer screen, sometimes bashing my face into it. Going back to the previous question that Sadat said about what quantum chemistry program do I use, sometimes some will work and some will don't, and you're just like, oh, why don't you work? And so for me, really just what I want is some validation that these crazy molecules that I've been studying are actually there, and I'm not just on some wild goose chase. So I was very lucky, very, very lucky, that an experimental group did a search for ArOH plus after we did the predictions of that, and they were able to find it. To narrow it down, of the molecules that I've given you here, the ones that I really, if I had a wish list, would really want astronomers to look for would be the C4H2 isomer that I gave you that has that cyclopropyl ring with that extra carbon on the top. For sure that one, because you can see it rotationally and in the infrared. And that's probably going to lead to larger pH formation. And it may have something to do with how pHs progress from small molecules to larger sheets. The other one would be one of those insta-type monomers. I think one of those would be really, really interesting to find. Again, they have very large dipole moments. They have very active infrared features. So those that have those three, the C2V, Forsterite, Instatite, and C4H2, those would be the three on my wish list. So thanks for asking. Awesome. Let's keep going. All right. So Maria Drozdeskaya has a question. So thanks, Maria. We've worked together on a couple of projects. So she says, concerning O plus bonded to water as a source of O2 and 67P, at what physical conditions would water and O plus form a bond? Also, this would require molecular water and O plus to exist at the same time and take place at some point during star and planet formation. You're absolutely right, Maria. It may actually be better that you have H2O plus and oxygen to form the covalent bond in O2. I didn't mention this. So for me, as the quantum chemist, the actual reaction mechanisms to form that, I'm not totally sure what that would be. For me, I was thinking, hey, if I just generate the spectrum, maybe somebody will go look for it, and then they can tease out what the conditions would need to be. But the thing that's interesting about that particular molecule is that it does have an excited state. There's this crazy excited state that pops in where you move an electron into a quartet state, and I think it's at about 600 nanometers, so it's a very low-lying electronic state. And if you excite this at about 600 nanometers, then the electrons reform, and you actually make O2 plus an H2 if you allow it to optimize to that excited state. And so that might happen, I don't know. But for me, I was like, oh my gosh, we formed an O2 bond. So I'm not totally sure what those physical conditions would be, is the shorter answer. Okay, so Grace Ni says, I wonder what makes O to preferentially bond with C to form organics versus to bond with Si and magnesium to form inorganics. Have I looked at Fe? I have not looked at Fe. Iron is terrifying from a quantum chemical perspective. And then have I looked at the relationship between oxygen fugacity and types of organics, HCN versus CO? So these are good questions that we have here. So the first one, you say, what makes O to preferentially bond with C to form organics versus to bond with Si? It has to do with what the environment is from my somewhat naive perspective, I would think. I'm not going to tell you that I'm an authority on this, but from the way I understand it, when oxygen forms in a star, carbon and nitrogen are forming simultaneously. And so carbon and oxygen are close in proximity to one another. And so they're going to, when they're formed in the star, and so as they outgas from the star, they're going to be close together. And so that's what's going to make them form together. Now, if you have a larger star and you are then able to go on in your alpha process burning in stellar nucleosynthesis, and you can go from oxygen onto neon and then magnesium, and then just add 2 all the way through until you get to iron, then you're going to get silicon and sulfur. They're going to form at roughly similar times. And so in order for the silicon to interact with the oxygen, in order for the magnesium to interact with the oxygen, as the shell of the star, especially the dying star, moves out, then you have to get mixing of those layers and some turbulence to go along with it. And so I would say that probably the reason why it bonds preferentially is because by the time silicon and magnesium come along, much of them are taken up with carbon monoxide. Then whatever oxygen is left over in water or hydroxide, that is available to bond. And we've done some studies that have shown that you form very strong bonds with oxygen, with the oxygen and water, with magnesium and silicon, and then to the point where even those hydrogens start to leave the system. Your second question, the relationship between oxygen fugacity and types of organics like HCN and CO, I've not looked at that at all. It's an excellent idea. Oh, you're right. Okay, so then Ryan has another point. Ryan Galinkin comes back after my response. I did forget to say that water would be abundant. Yes, absolutely, Ryan, you're right. Water would be one of the most abundant, but if I'm not mistaken, it's not as abundant as HCO+. It's a little bit further down. Okay, so Lorinus, I hope I'm saying that correctly, says, what would you have any advice or recommendation for scientists who want to pursue a career or PhD in spectroscopy and astrochemistry? Wonderful question, one of my favorites. The best thing that you can do if you want to pursue a career and get a PhD in spectroscopy or astrochemistry is it's all about people. You know, we talk about science being this logical endeavor, but it's really all about people. And so it's finding an advisor in a PhD program where you think that the research that's going on there is interesting, where the person who would be your PI is somebody that you can get along with, someone that you can work for. Because some things in graduate school are not fun and they're not easy to deal with. And having an advisor that you work with, you know, it's like any relationship. You're going to have times where you get along well with them and you're going to have times where you don't. But it's all about finding a person. And when you find an advisor and you've talked with that person and then looked at their research and interacted with them, and then you go on to maybe do a PhD in their group at their university, they're going to give you opportunities. They're going to introduce you to people. They're going to give you connections. You're going to go to conferences. And so the best piece of advice that I would do is look for PhDs in the area PhD programs that have things in the area that you want, and then find researchers in those programs, talk with them, interact with them, get to know them a little bit, and see if you want to work with them. Then the next best thing to do at that point is to, you know, astrochemistry, we don't have, Brian and I were talking about this before the waiting room opened, we don't really have a go-to textbook for astrochemistry at this point. There's a lot of really good textbooks, but none of them have really kind of risen to the top of something that gives a holistic explanation of everything. And so really the thing that you can do is just read papers, read review articles, learn astronomy, basic level astronomy, and obviously stick with the chemistry too. I would argue, and I'm biased, that if you want to do a career in astrochemistry, understanding the chemistry is probably a little bit more important, but you have to know enough astronomy to know why you're doing what you're doing. So that would be what I would say, Lorinus. Okay. Helgi Raffen says, with your theoretical approach, which saves on computer time, can you estimate an upper limit of the molecule size you can look at within a reasonable amount of time? I'm thinking in terms of PAHs. Could it be coronene, circumcoronene, or circumcoronene? Now we're getting into big PAHs. So there's an approach that I'm working on right now that's using fast quantum chemical techniques that have been forced to work on certain classes of molecules. With that, we think we can get up to maybe circumcoronene. If we're able to work on scaling factors, we could probably, and we're talking about getting accuracies that make it reasonable to do experimental comparison. If we're able to do harmonics and then scaling factors from that, we could probably go to things that are significantly larger. There have been studies that Charlie Bauschlicker and Alessandro Rica have done for several decades now at NASA Ames, where they have looked at, you know, just doing B3LYP with a small basis set and then doing scaling factors, standard scaling factors on those vibrational frequencies. And they've been able to generate spectra that fall within the range of what we would expect those pHs to be. But when it comes to a finer tooth comb, we need something a little bit more accurate. So we're working on some things. Hopefully we could get to circumcoronene, but you know, we're still talking about potentially hundreds of millions of points. Maybe we can do some derivatives, some analytic derivatives to lower that, but we'll see. Okay, cool. So right now, a lot smaller than coronene, but we're getting it up to hopefully circumcoronene. Okay, all right, so Grace has one more thing to say. Certainly don't mind more questions. The recent spectroscopy suggests that lots of ammonium on the surface of 67P. Yep, I was reading about that actually earlier today, as a matter of fact. Why would ammonium doesn't get oxidized by O2 on the surface? In situ measurements of dust grain from 67P suggest the presence of macromolecules. How likely is it to form large organics, like tripeptides in space from a thermodynamic perspective? Oof. I don't know. The answer to that question is I'm not sure. The best example that I can think of is when you have carbon monoxide on a surface. You just keep adding H2 to it and hydrogen atoms until it eventually forms methanol. I don't really know. That's a little bit outside of the things that I've studied about ammonium salts and ammonium getting oxidized by O2. I imagine it happens pretty straightforwardly because you're going to make, if you have O2 and ammonium, you're probably going to make water and ammonia and 1/2 O2. But if I had to guess, and this truly would be a guess, it would be that the ammonium salts are fairly stable, and so they just simply don't react as well, and they probably get covered up by other things. But again, that's a guess. I'm not totally sure. Not totally sure. Whew, all right, excellent questions. Thank you all. So I think at this point, I'll turn it back to Brian and see if he has any following statements. But before I do that, I just want to say thank you to all of you for being a part of this. Thank you for your questions. I had a blast. I hope you all did too. Thank you, Brian.
Thank you. And so we'd like to again say thank you to Dr. Fortenberry for giving this talk. Excellent talk. It was way beyond anything I could have imagined. It was amazing. I'm so thankful that you were willing to give this talk and stay so long to answer questions for us. We want to thank the audience for joining and having this amazing response to our webinar series. You guys have been a great motivation for me and Katie both as organizers. The amount of feedback we get from our registrants is phenomenal. And we want to let you guys know that coming up this Thursday, we do have the next talk, which will be by Dr. Micah Scheibel from Georgia Tech in radiation processing of dust, asteroids, and moons. What does it do and what can it tell us? So that'll be Thursday, May 21st at 1 p.m. again, EDT. So thank you again to everyone, and hope you continue to tune in and enjoy our series.
All right. Thank you all.
Take care. Bye, everyone.